Today I'm going to talk about the paper the way we worked on improving clip using visual grounding and LLM-augmented clip embeddings. Mostly, like you probably know that traditional recommendation system suggests product based on broad categorical similarity, often missing fine-grained visual coherence. In contrast, our visual recommendation system, powered by visual grounding and LLM-augmented queries, improve the relevance and basically enhance the recommendation. Also, like as you can see from the right figure, it highlights how our model enhances search. Like basically traditional keyword-based search may yield inconsistent results when dealing with complex queries like AROC with pet big or domestic pet shit. Our model effectively aligns textual queries with the most relevant visual content, ensuring that search results are not only textually but also visually accurate. These improvements validate our approach superiority and meaningful retrieval. And this slide shows some of the motivation behind our model. What we can see from here is that models like CLEAP mostly trained on open domain data set, and mostly they lack the basically e-commerce specific data which are useful for e-commerce recommendation. And we also know that most of the e-commerce data set is not very clean, and most of the images are noisy, and also the clip, also like the textual data, again, they are noisy. So another motivation behind this work is that clip is not always doing the best job when dealing with fine-grained attributes. For example, when dealing with a shirt, it might have a pocket, sleeve, neck, these kind of attributes that are specific for mostly like fashion items. And models like Clip don't do a pretty good job when we're trying to retrieve items with visually similar attributes. Here we propose a new algorithm how we can fine-tune models like Clip for e-commerce specific use case. If you can see from the upside, we not only use the entire information we have for each product. Like for example, from the text, we use the item description along with product type, item title, all metadata information that we have for text. We pass it through some sort of agentic summarizer that first refines, summarize and evaluates the textual input to come up with a better and the best representation of the query that can align pretty well with the image. From the image side, in order to clean the image and come up with, again, like a good image query, we pass it through some visual grounding models like grounding DINO with specific input types, like, for example, product type as a metadata, in order to crop and only focus on that part of images that most relevant to this. For example, here the image is we're looking for a dress, and we don't want to include other noisy image like product types included in that image. Then the rest is just training the model through contrastive learning. This slide shows the steps we take for summarizing the textual description and finding the best possible query. As you can see, in the first step, the entire text description of an item goes through a summarizer. The summarizer task is to come up with a summary of the text that are that do not have redundant information that we don't need it for the next step. And another evaluator agent, evaluates the performance of the summarizer and give it a score, and based on the score and suggestion, it goes to the next step, which is a refiner agent. Refiner agent refines and come up with a better query, and this process continues until we come up with the best suggestion and the LLM suggests that we do not need to proceed, or we meet the final number of iterations. On the visual side, we, again, like focus on that part of the image that is most relevant to us. Here, for example, you see that we only want to focus on the t-shirt. We want to crop the model, just focus on the t-shirt part and ignore the rest. That's very important. If we don't do that, when you perform retrieval, it may retrieve similar human in the picture, not the similar item. So that's also another learning that we have. This slide shows some of the results from the both fashion and home data sets. From left, you can see that all all are fashion items, and we tested on multiple different queries. Some queries are very close to each other, but different use cases. For example, Mickey Mouse for school versus holiday. It can really differentiate difference. Based on the queries, it can really retrieve relevant results. From the right side, you can see mostly home items that are items that are retrieved are visually very similar to the query. We have another set of test case, examples here that the input is the query input is image, and we perform retrieval based on the basically image retrieval on both home and fashion data sets. The results shows that, we have tested this model on multiple data sets. We only show it like Walmart data set here. We also experimented on Google Shopping data set. What we observed like VL clip, our architecture improves clips by almost like 100% on hit rate and MRR, and it's also performing better than other benchmark models. We have done another set of evaluation as well. In this set of evaluation, we used a little bit more stricter evaluation, and we focus on like using vision language models as a separate judge. And we started with extracting image attributes using like VLMs and coming up with a query that can represent the image. Then we passed this query to our index built based on different models, and we performed retrieval. What we observe is that VLClip, again, doing the better job than the other models, and it has the highest precision. And what we observe is that precision 1 versus 3 and 5, it's gradually going down, the precision for our model, because it means that most of the time the model retrieves the best result at the first position, which is not the case for other models like Clip. Clip precision at 5 is better than precision at 1. And we also perform another type of evaluation using the same like VLM. We retrieved similar items like using the image and passed the retrieved results to another VLM to do evaluation on just basically pure image itself. And again, the numbers shows that VLClip almost hits the 100% performance on this data set. I think that's it. Thank you so much.
Hello, thanks for the talk. My question connected with the inference time. Probably you can comment on how much in terms of comparison with fashion clip, for instance, your model takes for the inference.
Yes, for the inference time, we're mostly focusing on the image itself. We don't need the textual, like noisy data to come up with the inference. So on the inference time, we don't need the entire architecture. We just focus on the image part, and we do inference based on that. So inference time, we meet the latency budget of